How do we integrate the square root of tan x? This is an integral I was suggested to solve in the comments, so let's see how we can solve it. There doesn't seem to be too much to work with, so let's take the entire integrand to be u. If we differentiate this u, we get 1 over 2 times the square root of tan x. So that's promising, because we can use u in the equation for du. But let's not forget the chain rule. We'll have to multiply by the derivative of tan x, which is the input of the square root. And that's secant squared x. Okay, so to solve for dx now, let's multiply both sides by 2 times the square root of tan x, and then replace the square root by just u, the substitution we used. Now secant squared x can be represented in terms of u as well, because there is a fundamental trigonometric identity that relates tan x to secant x, and that's secant squared x equals tan squared x plus 1. So if we square u, we'll get tan x. If we square again, we'll get u to the 4 equals tan squared. And now if we add 1 to both sides, we can see that secant squared will be equal to u to the 4 plus 1. So we'll substitute that in the equation for dx, and dx will become 2u over u to the 4 plus 1. So now we can substitute for u as well as du, and we get the following integral: 2u squared over u to the 4 plus 1. Okay, but how can we solve this integral? It's a little bit easier, but it's still cumbersome. Can we use trigonometric substitution here? Actually, if we do, we will go right back to the square root of tan x. The original integral is trigonometric, so using trig sub will take you back to the original integral. We'll be going around in a circle, so that's not going to help. Instead, let's keep this algebraic form and do some manipulations that will allow us to work with it. Notice that the denominator is almost a perfect square. All it needs is an additional 2u squared, and then it'll become the square of u squared plus 1, right? So let's introduce this addition, but of course we have to make up for it by subtracting this 2u squared afterwards. Now we can take the perfect square, and then we'll have the subtraction of 2u squared to worry about. Again, 2u squared is not quite a perfect square in itself, but we can force a situation where we have a difference of 2 squares by factoring it in the following way. We can take the square root of 2 times u and the entire thing squared. Factorize this, we'll have u squared plus radical 2u plus 1 times u squared minus radical 2u plus 1. And now we'll use partial fraction decomposition. We have 2 irreducible quadratics in the denominator, so the decomposition for this is not very easy. We'll have to have a linear term for both. So au plus b over the first term plus cu plus d over the second term, the second factor in the denominator. So we have a, b, c, and d to solve for, and we need 4 equations. The way to get those is by multiplying throughout by the big denominator, giving us the following equation. 2u squared is identical to au plus b times the other denominator plus cu plus d times the first denominator. So now, to solve this, we'll need to distribute everything and group like terms. We'll have a plus c times u cubed, and then something times u squared, something times u, and then a constant term. And now we'll set up an equation for each degree of this polynomial. We see that the cubic term must be 0, because there is no cubic term on the left-hand side. So a plus c equals 0. Comparing the constants, we also see that there is no constant on the left-hand side, so b plus d must be 0. Comparing the quadratic term and using those 2 equations which we wrote down, we will get c is equal to 1 over the square root of 2, and then using the linear term equation accompanied with the equations we already wrote down, we'll get d is equal to 0. So we can conclude, of course, that b is equal to 0 and a is equal to negative 1 over the square root of 2. So that's it. We got the four constants a, b, c, and d. So we can remove b and d since they're both 0, and we can replace a and c by their values and factor out a 1 over square root of 2 outside. Okay, so we're making progress. But this is still not very easy to integrate. So what do we need to do here exactly? Let's complete the square of the denominator so that we can then use a substitution to solve the integral. If we complete the square of the first denominator, we'll get u plus radical 2 over 2 all squared plus 1/2. You can verify that if you expand this, you will get the same quadratic in the denominator of the integral above. And we're going to also complete the square in the second term in the integral. And this will allow us to use a substitution that will hopefully get us to a situation of a natural log or an inverse tan. Let's see. If we use w equals u plus root 2 over 2 for the first part of the integral, dw will be equal to du. For the second integral, we'll use v equals u minus root 2 over 2, same idea, dv will be equal to du. So we can substitute those, and the integral will become the following. Okay? We can separate the numerators because we see we have a combination of a constant numerator and a linear numerator. So we're basically going to have 4 integrals to work with. This is the combination of 2 integrals that give you everything to do with w. So if you separate the fraction, you'll take the constant over the denominator and then the w over the denominator, split it into 2 integrals, and this will be the result. And we're going to do a very similar thing for the v part as well. We're also going to split it into 2 integrals. One of them has a numerator of v and the other has a constant numerator. And for those of you with a keen eye, you can probably tell already that 2 of these integrals will be inverse tangents and 2 of these will be natural logs. If we look at this one, for example, we can see that a simple substitution will do the trick and we'll get a natural log. So if you take whatever, p equals w squared plus half, I don't want to keep introducing new substitutions, but this one is easy to solve. It's just that the numerator is w, not 2w. So we're going to have to just divide by 2 to make up for this difference of a factor, but this will be a simple natural log. Notice that I don't have an absolute value because the input of the natural log here is always positive. We'll do a similar thing for this integral. It's also going to be a natural log. We'll just have to divide by 2 as we did in the first case. So these are the 2 natural logs that we have. Now the other 2 integrals will actually be inverse tangents, but it's not extremely easy to see if you don't have a lot of practice because you need 1 plus w squared in the denominator or 1 plus v squared. So what we're going to do is factor out a 1/2 outside and do the same thing for the v integral as well. And the good news is that this 1/2 in the denominator now cancels out with the 1/2 outside the integral. And now what we'll do is group this 2w squared and 2v squared into a single squared entity, because that will allow us to compare this to the inverse tan situation. If we let s, for example, equals square root of 2 times w, then ds will be square root of 2 dw. If we rewrite this integral in terms of s, it will become the following. And now it's extremely obvious to see that this will be the arctan of s. And we can substitute right back. So s is the square root of 2w, so that's the integral done. The integral for v will be extremely similar, almost the same. It's just that there's v instead of w, and the integral will become 1 over root 2 arctan square root of 2 times v. So that's it, we're done. But now replacing w and v by their u equivalents and then going back to x needs a little bit of work. We can start with the natural logs, because notice we have two natural logs. The coefficients of both are 1 over 2 times the square root of 2. So we can factor this out and you can see that you have a difference of logs. We know that the difference of logs is a single natural logarithm of the quotient of the denominators. So we have these two logs over here, and these can be replaced by a single natural log of v squared plus 1/2 all over w squared plus 1/2. Dealing with a single log is easier than dealing with two. And now we'll start substituting back. So if we replace w by its u equivalence in the arctan, we'll get this, and then we can expand, giving us radical 2u plus 1. And then we'll resubstitute in the w of the denominator over here. Notice that the denominator now reminds us of the form of completing the square we did earlier. So if you expand it, you will get back that irreducible quadratic we were dealing with, if you recall. And then we'll replace v. We have u minus square root of 2 over 2. Again, if you expand it, you will get the other irreducible quadratic that we had. Let's replace v in the arctan as well over here. And we can simplify it very similarly to the first arctan we did, giving us radical 2u minus 1. If you remember, u was the very first substitution we did, and that was the square root of tan x. So all we need to do now is replace this instead of u, and we'll be pretty much done. So we'll have root tan x instead of u. Of course, we can combine the 2 and the tan x in a single square root, like this. And then we'll substitute it in the natural log as well, giving us tan x minus the square root of tan x plus 1 in the numerator, tan x plus the square root of 2 tan x plus 1 in the denominator. So that's it. Everything is in terms of x now, so we're done. All we need to do is to add a constant of integration c, which is basically the cumulative constant of all the integrations we did, and that's the final answer.